That's the one that didn't go to final exams. 21 paper, so that's the one that didn't go to final exams. So the mark scheme in this might have some issues, but not in the multiple choice. So let's just run through this. Okay, question 1. According to the Aufbau principle, electrons fill the atomic orbitals with potassium in the order, and we have options here. So potassium means that we're trying to get to here, number 19. Okay, so you're just going to run the order. So first one is your HE, so that's 1s. Here we've got 2s, and our next block 2p. None of this is helping because that's obviously, they're agreeing right up to 3s. Okay, and 3p, and so this is 4s. If you wanted to write a full proper thing, it's 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Okay, so correct answer here is C. Okay. Okay, question 2. Which of the following is not, in bold, so therefore important, a possible quantum number for an outer electron in an atom of oxygen in its ground state? So we've not got any promotion, we've not got anything moving anywhere. We are literally just looking at our oxygen over here. Okay, so 1s is already gone, that's not in the outer. We've got 2s that's been filled up, and then we've got 2p over here. So our 2s parallel and paired for that one, and looking at the electrons we've got in the 2p, we would go 1, 2, 3, 4 using Hund's rule for maximum multiplicity, so we've gone parallel then paired. So what we've got up the top end here in our outer electrons are 2 unpaired ones. Okay, so we're looking for which is not a possible quantum number for an outer electron in an atom of oxygen. So these are my outer electrons in the 2p subshell. Okay, so for a start, they're not asking you for n, which is your principal quantum number, and that's for energy level, it's all 2, but they're not even asking you for it. And they're not asking you for ms, which is your spin, which is either your plus a half or minus a half, also not there. Okay, so what we've got is orientation in the ml and L for your subshell type. Okay, so subshell, we just need to know your kind of, this is n minus 1. So our subshell here, where n is 2, so n minus 1, so that's possible because 2 minus 1 is 1. Okay, our orientation, now these are in the p orbitals here, so p is either, doing little doodles here, on the x, on the y, or on the z. That just looks like a fancy flower, but you know what we're saying for this. Okay, so this is either minus 1, 0, or plus 1 if we're trying to use just our numerical kind of orientations of that one. So 0 is possible, 1 is possible, so A is the correct answer. Question 3, still got up my same page from the data book, so it's been helpful for you. The number of unpaired electrons in a chromium atom in its ground state is, now, okay, so we'll go with the kind of the obvious wrong answer in a way first. Okay, so 1s is filled, and then 2s is filled, and 2p is filled. Okay, and then 3s is filled, 3p is filled, 4s, let's just go with it being wrong just now, is filled, and then we've got 1, 2, 3, 4 in 3D. So that would be 4, that's your 2, 2, 2, 2, 6, and 6. But chromium is one of your sneaky ones. Okay, this one here and this one here, your copper, both of them basically get enough of a payoff in terms of energy stability by promoting one of the electrons out of the 4s into the 3D to make it more stable. Okay, so what we've actually got is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5, which means if I look in the last bit here, I've only got 1 in this orbital box, and I never draw these long enough. 1, 2, 3, 4, make that 5, okay, and I've got all unpaired in this one as well. So the actual correct answer for this, a lot of people will have gone 5, is 6. Oh, yes, 6. Okay, question 4. Based on the information in the table, tell us whether something is less acidic, more basic, etc, etc. Right, so I've pulled the dissociation constants because that can sometimes be very helpful. What we're looking at here is the Ka. So this is the dissociation constant, which is, for ease, okay, we're just going to say that is products, concentration of products, okay, over reactants. Now, by reactants, obviously I'm meaning just reactants is this side and products is that side in the table, okay. So our Ka, so it's not even asking us to go to pKa, which is nicer, okay. As far as this one is concerned, you've got to think in terms of, well, the bigger that product bit is, the bigger the number, the higher the Ka gets, okay. And so that means more is dissociated to products, which also means increasing Ka means increasing strength of the acid. Right, so that's what you're looking for. You're looking for the biggest number. And then you just have to be careful with your scientific notation. So Z is your strongest. Okay, there's your strongest one there at 10 to the minus 5. So Z is stronger than Y, which is stronger than X. That's basic. So that's your, I don't want to say basically because obviously you're not going to talk about acids and bases. So this is your acid line, okay, from the strongest to the weakest. So then you just work your way through. X is less basic than Y. So is X less acidic than Y? No, so that's not true. Okay. X is more acidic than Z. Again, nope. Y is more basic than Z. Yes, because it's less acidic. And Y is less acidic than X, just to check. No, because it's more. Okay, there we go. C is the answer. Question 5. Okay, this one, when you look at it, you automatically kind of gravitate to thinking it's going to be your delta G is equal to your sum of delta G products minus sum of reactants. But it's actually not that. It's effectively a Hess question that you've been given to do, but not the way you normally do it. Okay, so this is actually, if I make this one A and B, just to do this algebraically, okay, my delta G is going to be a half A plus a half B, because I'm going to swap that over. So just to be clear what I'm doing here, I need, this is basically become my target equation. And these two up the top are my data equations. I need the data equation to be fixed to my target equations. So I've got 2C here, and I've only got 1C here, so I'm going to have to half this number to put this into the equation. And then I'm looking for zinc oxide. Let me get a different colour. Okay, here's my zinc oxide. Okay, it is not only 2 and I need it to be 1, but it's also on the wrong side. So I need to flip it over, so I'm going to change this to a plus and I'm going to half it. Okay, so if I do that, my sum should read as 2 minus 237.5 plus 170. Just pop it in the calculator and get your answer. Okay. Right, question 6. Which of the following represents the enthalpy of formation of a compound? This is a pure definition thing. If you're looking for the enthalpy of formation, okay, it must be 1 mole of the substance that you're forming. And most importantly, in terms of how they tend to give the questions, it must be from its elements in their standard states. Now, I didn't actually pull the databook page, but you could pull the one that's melting and boiling points just to check what the standard states are. So first of all, let's get rid of this one because it's 2 and I need 1 mole. Let's get rid of that one because it's 2 and I need 1. And now we're down to 2 options, and you're like, right, okay, that's 1 mole of a substance. I'm halfway there. Elements in their standard states. Yep, magnesium and sodium are both solids in their standing states. Oxygen is a gas. Bromine is not. Bromine is a liquid. So there we go. Question 7. Kinetic data for the reaction between bromate ions and bromide ions in the presence of hydrogen ions is shown below. Okay, this is a rate order equation that you're trying to figure out. The only way you can do that is by doing pairs and figuring out what you're looking for each one. Okay, so which line of the table shows the order of reaction for each one? So let's start with finding things that can pair up. So if I take experiment 1 and experiment 2, everything is the same except for a doubling of the bromate ions. Look at that, and then look at what we've got over here, and we've got a doubling here. So basically, if I double, oh sorry, slightly scribbly, if I double these guys, I double the rate. That you should recognise as first order, so I'm like, okay, these are potential so far, but not D. D is now out of the running. Okay, for my next one, different colour. Okay, so for my next one, I am looking for my bromide that I can actually work with. So this time, if I take these two, everything else stays the same, and I am now comparing these two here. Okay, and what I've got is if I double this, I am getting yet again a double of that. So these guys are first order as well. And the last one I'm looking for is hydrogen. Okay, so hydrogen this time, I'm just going for as many different colours as I can possibly throw in here. I'm looking at experiment 1 and experiment 4, because that's got a change here from 0.1 to 0.2. Everything else is the same between 1 and 4. So I'm going from 8 times 10 to the minus 4 to 3.2 times 10 to the minus 3. So that one, okay, if I double my hydrogen ions, I am actually quadrupling my rate, so that is second order. So B is the correct answer. Question 8. Which of the following graphs would be obtained for a reaction that is zero order with respect to reactant X? It's not the nicest question. You have to be really quite careful about how you read it. Okay, so if it's zero order, what that's saying is that the concentration of X has no impact on the rate in terms of if you double X, you double the rate. So you've not got the same things as you had in the last question. So I suppose reasonably okay that they've given you that information. Okay, so what you want to do is kind of look for things where that's basically got nothing to do with it. Okay, so in the first one, what you've got is basically a first order link, because what you've got is as you increase the concentration of X, you're increasing the rate. So it's not that one. Okay. In B, what we've got is something quite strange. So basically what we're saying here is that if you're increasing the concentration, you're decreasing the rate, which is not, again, definitely not zero order. This is an impact one, and also not something you would look at all unless you were looking at some form of inhibition, which is not at all what we're dealing with, so no. C, this is basically just no reaction at all, because what we've done is we've flipped over these axes, and now what we're looking at is the concentration of X, which is not changing over time. Okay, which would mean nothing's happening to it. In D, however, I've got the concentration of X, which is just decreasing over time, and it's in an absolute straight line, so it's not having more of an impact at different points in the X's concentration, so that is zero order. I don't think it's the nicest question. You've got to be really careful. Question 9, still on rates. For the reaction 2P plus 2Q goes to R, the rate equation is, and you're given as rate equals a rate constant, concentration of P squared, Q squared. Which of the following, sorry, not Q squared, just Q. Which of the following shows a possible mechanism for this reaction? So what we're looking for here is a slow step, okay, because that's the only thing which is going to be part of the rate equation. Fast steps don't get into the rate equation because they're fast, and slow steps are what make things happen. So actually let's just make our life a bit easier and say, right, okay, so I'm only looking at this slow step here, I'm only looking at this one here, I'm only looking at this one here, and I'm only looking at this one here. Okay, so I'm only looking at the slow steps, I'm ignoring the fast steps entirely. Okay, then you look at the rate equation and you look at it and say, I need 2 P's and I need 1 Q. That's what, because we've got P squared and we've got Q just as a single thing. So now you just look at your slow steps and find one which has 2 P's involved and 1 Q. So it's not A, B's good. And just to check, it's a P and an R, so it's definitely not C, and it's definitely 2P and a Q oh sorry, looking at the fast here, I was thinking that works, but that's the fast. Q and R for that one, so that doesn't work either. Okay. Question 10. For the reaction given below, okay, which line in the table is correct? So we've got nucleophiles or electrophile as the option for the OH minus, and then we've got something about the alcohol that is produced here. So this is basically a bit of drawing stuff out, okay? So what we're looking at is CH3, CHBr, CH3, okay? Plus we've now got our, so we've got an OH minus, which is going to do an attack thing in here, and we end up with CH3, CHOH, CH3. Okay, so the easiest bit is going to be deciding what that alcohol is. So, because it's really higher. Okay, the carbon which has the OH on it is attached to two other carbons, so we can confidently say that that is secondary. Okay, right, what we now have here is a substitution reaction. Okay, so substitution is for this bromine for the OH. Okay, and to be honest, there's a little bit of you just need to, it's easier just to know this one. That is nucleophilic substitution, because that's what we have with your alkanes and your halides. Okay, so A. Okay. Question 11. Which of the following reactions involves homolytic fission? Okay, there is an easy way for this one to work for you, which is if you recognise straight off that homolytic fission is part of your free radical production. It's pretty much the only one you know. It's the only thing you've got anything to do with it. So it's free radical substitution, and so therefore we're looking at the halogen. Now you'd normally expect it to be a ClCl, but in this one we've got a bromine. There is homolytic fission, because what you've got there is in the bromine we've got half going that way and half going that way, with we're losing little curly arrows. Okay, the other ones, just to be clear on what we're looking at here, so you've got electrophilic substitution down here to make your substitution, that's a dodgy spelling. You've got an nucleophilic substitution, the same thing that you just had before. I feel that I'm just misspelling things terribly today. Nucleophilic, there we go. Substitution. And at the top, we've got an addition reaction, which is an acid catalyzed one, but again, not involving any form of homolytic fission. Okay, so this is your addition, involving a carbocation intermediate, to be precise in that. Okay, so yeah, find your free radicals. Anytime homolytic fission comes up, that's what you're looking for. Okay, which of the following has the fewest sigma bonds? So you need to know that basically singles to singles are okay, but anything with a double is not. So you could just go with logic here. This hexane is an alkane, has the maximum possible kind of ones that you could have. If I draw it out here, 1, 2, 3, 4, 5, 6. Okay, so we've got every single one of these is a sigma bond, okay, created by your sp3 hybridized. So we've got 19 bonds in here. Okay, now anything which removes hydrogens from this basically is going to decrease the number of sigma bonds that you have, increase possibly the number of pi bonds that you have. If I make it hex 1ene, I'm basically taking this to another 6. If I put a double bond in here, I'm reducing down the number of sigmas that I can have, okay, by 2, basically by sticking in a pi bond. Okay, so that would be taking me down to 17. Okay, if I take it up to a triple, not even sure I need to draw all of these in. 1, 2, 3, 4, and 1, 2. There we go. Okay, I've knocked out another 2, so I'm down to 15. And cyclohexane would be the equivalent of taking out the 2 hydrogens at the end to make my 6 work. And then stick on my hydrogens all the way around rather. So that one, I'm not doing quite as much damage to the number, but it's still lower. So my maximum here is hexane, and then we've got cyclohexane, and then we've got hexene, and then we've got hexyne. So C. Question 13. Propyne undergoes addition reactions, and we've got a nice little picture of propyne. Assuming the reaction between propyne and hydrogen chloride follows Markovnikov's rule, a possible product could be. Okay, so Markovnikov says, basically, hydrogen goes to hydrogens. Okay, and whatever the other thing is goes to the other things. So whatever has the greatest number of hydrogen substituent groups gets the hydrogen. This one is going to get the hydrogen. And the other one is going to get the other thing, so it's going to get the chlorine. And we're going to obviously get rid of one of the triples, rather, to make it a double. Okay, so what we've ended up with is going and Cl. There we go. Okay, so counting with, so this is propene. I don't need to put a number in the ene because the only place I can put it is on carbon 1, and the chlorine is on carbon 2. So 2-chloropropane. Sorry, 2-chloropropene down here. That's it.